folks, we really want to welcome you. My name is Raj Manchanda. I'm the Chief Technology Officer at SAMPE. For those of you who don't know, SAMPE is the Society for the Advancement of Material and Process Engineering. We're very fortunate to have Professor Nandika D'Souza with us. And, the topic is a very compelling topic. Before we started, SAMPE is a global organization. And before we started, we were reviewing the attendance list, and I saw colleagues from Argentina, Mexico, Australia, New Zealand, Canada, Belgium, England. So that's what this is all about. We really want to make sure this global technology exchange that Nandika and SAMPE were partnering to bring to you, it really is an effective way, now that we aren't on planes right now, but also on the webinar, we have professionals from Boeing, Airbus, Kohler, Solvay, Evonik, Infosys, John Deere, Eaton, NASA, Milwaukee Concepts, Michigan University, obviously Nandika's school, University of North Texas, Dayton, Texas State, McGill. So we're really pleased that you've all been able to join us. What we're going to do is I'm going to pass the baton over to Nandika soon. I'll do a brief bio. We'll get going. And we ask that you really utilize the chat. Especially we have such a global audience. Utilize the chat. Let us know what you're thinking, your comments. We have my colleague, manager Brianna on the line also from SAMPE headquarters. She's going to help out. But I will start by introducing Nandika, and then we'll pass it over. Professor Nandika D'Souza is Regents Professor of Mechanical and Energy Engineering Material Science at the University of North Texas. For those of you who are joining us from overseas and in the country, she's right in the Dallas area. So everyone knows the Dallas area, and she's in a beautiful part of the country. I forget what the saying is, but it's one of the largest metropolitan areas in the nation. Recently, Toyota moved out there, so a lot going on in that area. Nandika's research area focuses on multifunctional materials for engineering solutions with multidisciplinary partners. She's highly accomplished, and we're really grateful that she could carve out some time amongst the teaching that she's also responsible for this semester. She's a fellow of the Society of Plastics Engineers. She received the 2015 Distinguished Engineering Educator Award from the Society of Women Engineers. She's a life member. I'm not going to just read off the acronyms. SWE, you guys know that because we mentioned it's the Society of Women Engineers, but SHPE is the Society of Hispanic Professional Engineers. NSBE, that's the National Society of Black Engineers, and the Girl Scouts. So Professor D'Souza, we're really fortunate to have you spending some time with us. And one of Professor D'Souza's goals is to transform the demographics of engineering leadership. This is really for all of us. Look around yourselves, look at your workplaces, look at your communities. We all need to do more to make sure our leadership is diversified, because at the end of the day, you get a better, diverse solution, and that helps the bottom line. Nandika has a few patents, 6 book chapters, and over 93 peer-reviewed journal publications, and over 100 conference proceedings and presentations. She's faculty advisor to SAMPE, our organization, at the University of North Texas, and is the deputy Technical Program Chair of CAMEX 2021. CAMEX 2021 will be held, if everything goes accordingly with a vaccine rollout, in her backyard. So we look forward to many of you joining us in person in the Dallas area. CAMEX typically attracts thousands of attendees, maybe 7,000 to 8,000 from around the world, and maybe 500 to 600 organizations who share their latest composite innovations. Nandika, I'm going to pass it over to you, please. And I really appreciate again that you joined us, and let us know, on this great topic. We look forward. Thank you.
All right. So let me know if we are, let me make sure I'm in slide. Show. Okay. If we aren't good to go, let me know verbally.
Nandika, you want to hit, sorry, do you want to hit the presentation mode as we did last time? So the speaker, it's a full screen.
Oh, I see what happened. 1 second. It reverted to the
It reverted,
same thing.
yeah. You could probably go to the three dots. Thank you.
three dots and
Presentation, yeah.
good.
Perfect.
Okay. All right. Welcome, everyone. I'm going to talk about our journey in sustainable forms and sandwich composites. It's a win-win solution, which I hope we can do more and partner more in the future. We've been doing work on this for the last 10 to 12 years. And so I definitely want to acknowledge the contributors to the work, and I've tried to add them in each slide. So my general perception is that what we're talking about is reflective of a general situation that we're always presented with a false choice, at least given that we have a global audience. I'm feeling I can share that I was always a little surprised that there was an expectation that scientists and engineers would not be artists. And I know that there are so many great scientists and engineers who are musicians, painters, etc. And so I just keep hearing this false opposition that is presented to us. The other area I'm very interested in is in environmental impact, and people say, oh, you can't support the environment while advancing production and return on investment. And as Raj shared in the beginning, I'm very passionate about inclusion, see it as a win for all. And people say, oh, don't talk to me about hiring, etc. I'm just focused on my profitability. I don't see these as choices. I think we can do both. So that's kind of the heart of today's journey. And I hope if you're feeling kind of defensive on the right side as far as being a scientist, engineer, wanting to be productive, and having industrial products, you'll feel very comfortable with doing societal impact concurrently. So as we go to, give me one, okay. So the moral of the story is, for those of you who are aged enough to remember the saying, can't we all get along, which was from a couple of decades ago. I'm very attracted to a few books published by Dieter Helm. There's a good YouTube video that I encourage you to see. And he essentially is asking us to reflect on whether all our legislative approaches are having as much of an impact as we think. I like this phrase where he says there's almost a race amongst governments since the 1990s to show who's more active in climate change legislation. But throughout all this extreme discussions, there's actually concurrently a constant growth in carbon emissions. And even now with coronavirus, we're adding 2 parts per million into the atmosphere. So definitely we're just, all the legislation, there's a mixed bag in terms of effectiveness. And the point that this is actually an excerpt from that YouTube video, I thought I liked his presentation. It fits with some of the themes we're going to talk about, is that the battle is always between sequestration and emissions. So I'm going to explore this middle ground of actually using sequestration products to fulfill our engineered solutions, and an approach to manufacturing that may utilize some of the sequestered sources. He's had a kind of a controversial history. I think he boldly in 2011 pronounced failure of the current approaches, but this year has been awarded a number of awards, particularly in Britain. So here's our journey at the University of North Texas. We have designed our approach on the Cradle to Cradle book that has been published by William McDonough. It's frequently associated with the rubber ducky, which is the certification when you achieve C2C acceptability. And so what we like to do is that you can have you have your plants, and you have fiber, you have a fruit product, you have seeds. You can actually, from this, you can harness materials that can either you have fermentation, polymerization, processing, you have extrusion, and you can have building products, lubricants, adhesives, composites, concrete, packaging, textiles, everything. So multifunctional products can be realized through this approach. When you're done with using it, you could have a compostable, biodegradable system that could then convert back into plants. So the both circular economy concepts, the cradle to cradle concepts, all come together in this systemic solution. The important thing to realize, we have to have products. Having no emissions can sometimes mean there's almost like a negative communication or with regards to doing engineered products. So people are almost like feeling like, I'm just going to get penalized if I actually produce something. But we need things to be used. And so there has to be some kind of an intermediary.
Professor D'Souza, sorry,
Yeah.
on that note, you talk about the products, which is really hits home because this is a huge industry, it's a business. What would you say to conventional polyurethane-based producers? We're not trying to eliminate them, right? I mean, how would you position your innovations to conventional manufacturers?
So polyurethane is a good example. You can use now very good green chemistry to produce 3/4 of the polyurethane could be sourced from biomaterials. And so long as you're using a product, the biomass is a zero carbon footprint contributor. And it's in its before it's processed is a carbon capture system. So there are solutions, and definitely every problem has a solution for it.
Excellent. So it's a partnership. Thank you.
Good partnership, scientists. So definitely you want to reach out to, I want to achieve this end. What are my options? Can I come up with an economic tax option that would actually give me credits? So definitely a very good question, to be honest. All right, so where we are, as Raj mentioned, we're here located in Texas and in the Dallas-Fort Worth area, and we're surrounded by a good aerospace engineering workforce. Our SAMPE DFW chapter, University of North Texas as a chapter, a number of universities. So a lot of good excitement and footprint for SAMPE. Our university has two campuses, one which we call the main campus, but we are located 5 miles north in a beautiful facility that used to be the former Texas Instruments facility. And so we are a single building with College of Engineering in it and abundant manufacturing and characterization facilities hosting all the applied engineering you could ask for. Our own laboratory, we have two areas we use. We have a good characterization facility, and we have a very good manufacturing facility, which includes the ability to make 6 foot by 8 foot sheets of compression molded materials. And we can take products right from the source, convert them, process them, make the finished product, and characterize the application performance metrics. So here's some of the backdrop. We started out with looking at just our natural renewable fillers. So what happens is that the two plants of interest is Kenaf and Hemp is our new area. It was restricted for a while, but now it's becoming more available. The advantage of that is within 9 months, you basically get your source crop. And throughout the process of growing it, it is definitely contributing to decreasing emissions and increasing sequestration. So renewable plant resources that have a quick time to growth can be harvested and used are already a good alternative to even the longer term wood-based products. So if you look at this Kenaf or hemp, etc., you'll find that you have a skin area, which is what you can convert into these fibers, which are bast fibers. And you can see they have a similarity to the glass fiber. And the core material can be reduced either by itself as, bamboo, or you could actually grind it up. And these ground materials, the material is porous, so you have excellent sound absorption, thermal insulation, etc. So we have looked at some of that. And then the fiber in fiberglass relative to the other natural materials, you have a strength to weight ratio than a specific stiffness that gives it some advantages over as a fiberglass replacement. So right there, you see you can replace your synthetic materials through materials that will give you good carbon credit. Then you have, when you look at these plant materials, if you really looked, you just took the plant out and you looked at it under a fluorescent microscope, you'll see this beautiful porous structure. The blue corresponds to the lignin in it. But if you look at industrial processed fiber, this is what you would see, which means that the porous structure that nature gave it has essentially been destroyed. So using chemical processing approaches pretty much wreaks havoc on the porous structure that we thought was so good for sound absorption, thermal conductivity, etc. So we looked at that, and what we wanted to do was analyze what are the contributors to mechanical performance in terms of structure, chemical composition, and what can we learn from these natural fiber architectures that could possibly give us a win in terms of composite performance. When we started out, people would disdainfully think about, oh, you've got a natural composite. I don't want to hear about it. I'm not interested in these biocomposites, etc. It was because mostly people use this very wrecked fiber. The material is very porous on the surface, very bad in water absorption, and almost a death trap for absorbing all kinds of microbes, etc. So we looked at that and we worked with the biology department. We have a great team on campus crossing multiple departments. So we connected with them and we did one of our first investigations, analyzing the structure of the fiber and what are the constituents. And when we went forward, we actually found in our, we were able to create a natural fiber that would have, this was our porous material from alkali or sodium hydroxide treatment, which practically is the approach used for converting your cotton from the plant to a cotton that you would use in your textiles. And here you see a substantial drop in moisture absorption by using a bacterial approach. Let me also give you this to mull on. The cost of the bacterial relative to the sodium hydroxide alkali process was literally down to 2 cents. So it's a very cheap process, and bacteria turned out to be a great win for us. Modulus wise, we were able to show that we were able to retain our modulus over time. And you can see that two aspects. One is you're retaining your mechanical performance, and the other one is the property is substantially above what we call the wrecked fiber material with sodium hydroxide.
Professor D'Souza, sorry,
yeah.
Another interruption. So many of the organizations on the call are multi-billion-dollar conglomerates, and they probably can do similar experiments. But what about smaller and mid-sized companies? Can they partner with UNT and other universities if they don't have the biomaterial expertise?
Absolutely. So we have a very good tech transfer. We have a biodiscovery institute that emerged out of that system that I showed relative to that cradle to cradle. And we have, I personally think we're looking at the we are situated in the center model, so you can definitely work with us to run tests, measurements, source your materials, life cycle analysis, down from production all the way down to degradation. We have composting, all the kind of facilities.
Excellent.
So
Thank you.
yeah. And then we had the other aspect we said is what made all this performance possible? Well, when we found out is that by using this bacterial approach, the second segment we were able to retain in our fiber is the functionality on the surface. The functionality on the surface helped us to have a reactive surface that gave us phenomenal mechanical properties. And again, we're blessed in our university and in our institutes that we have controlled places where we can actually develop unique growth processes, etc., that can then be translated into large-scale agricultural solutions. So one of the other things we did, because we said, what is wrong with all these fibers? Can we overcome all the limits? Well, water was a big problem. So we said, what do you know? We can actually treat the fibers and you can have complete water repulsion. And we can also treat the fibers and we can make it flame retardant. So we were like every property that you could think of when you go like, oh, that's not something I want to use. We were determined to see what's the solution to it. And then we said, because plant-based materials are definitely not a popular solution, we said, what if we could make a carbon fiber from a plant source? So one of the challenges right now is people have been trying this and they use waste products from paper and pulp industry. And that carbon has been very inferior to the commercial pan-based carbon. Well, we were fortunate. We had a National Academy of Science member, Professor Dixon, and Chen Fang, who joined the university, and they had what they call a linear lignin. And linear lignin helps you to process it just like normal polymer chains. So we looked for carbon, and that's one of the patents we have is on carbon from this linear lignin. It becomes, you got a good yield from it. We were able to get single crystal carbon out of this material relative to what we call the kraft paper and pulp lignin that was very amorphous. And the crystalline carbon allows you to have a very conductive carbon. Where do you find that useful is all your electrostatic charge dissipation carbon solutions that you are using. You can actually use plant source carbon materials that can then give you additional options for your carbon credits. So that is another valuable solution, right, available. And here you can see we compared, what happens, can we blend pan with our C-lignin, because pan is really good for processability. And we found, yeah, you can both make a pan lignin combined fiber. You can also get a conductivity relative to that pure C-lignin, is this called PCFA. So that kind of was a great experience. And then we said, all right, we've done a bunch with fibers. What can we do with an application? Buildings represent a very big carbon footprint consumption platform for us to consider. So we looked at that and we said, what can we do if we could make, the panel? Sure, we can take sandwich composites, make our skin. What can we do to the insulation? So we looked at it, and if you look at this, the first approach was kind of to your polyurethane vendor. We looked at taking plant-based materials with polyurethane. So by replacing the fraction of polyurethane, decreasing the polyurethane fraction, increasing your biomass fraction, you are able to decrease carbon footprint from that polyurethane. And we looked at it, we did have to come up with a new manufacturing approach for the polyurethane, which is in this publication. It's kind of a cool idea. It's basically you work on controlling expansion ratios and create a pressure against which the foam would expand rather than free foaming. And that ended up giving us very good mechanical properties for this. You also decreased your weight. So you got lightweight foams that are also great for your fuel efficiency applications in terms of manufacturability, transportation, and we got a high mechanical performance solution. So that was one option. And we also use recycled foams. I'm going to just skip that. We use also a soy-based polyurethane, and this one is a commercial product. You can see that polyurethane, this is the concern, is that in the last stage, returning it to ground, not at all compostable, but the soy-based polyurethane, where you're replacing one of your polyurethane fragments, you're able to get it past the compostability standard. So combining Kenaf core with the soy foam is the way to get your best of both worlds. You improve your polymer and you can get it into the compostability range. So that is a kind of was a good experience. And of course, we're constantly challenging ourselves. So we've got this plant source. We figured out a way to make it very cheap, microbial processing, so zero chemicals being used during manufacturing, high throughput approaches. And then we said, what about the foam? Can we actually try environmentally benign manufacturing? And so we approached again with our buildings. We had the fiber, we had the form, and we did a farmer academic industry partnership, which is what is our, that has these representative elements. And we created this partnership for innovation program. So here's our environmentally benign processing fluid. And you look at supercritical fluids here, and this is carbon dioxide. So you've got this CO2, and can you make use out of CO2? Let me give you a slight bifurcation. I'm focusing on foams, but there is plenty. A wonderful collection of articles early this month came out just related to options to using CO2 for synthesis of chemicals. So here you have the CO2 foam, and what CO2 has is a unique solution, which means that through its using the temperature, pressure conditions, it can convert from gaseous to a liquid state. So at 31 degrees, you can actually apply pressure and it will flow like a liquid for you to use as a processing fluid in your foaming solutions. You could pair it to an extruder, or you could use it in a batch process. For our building applications, we have used the batch process. So we paired up again, Dr. Zhu and Dr. Tao. We worked as a team and we were able to look at the full story, life cycle analysis, carbon footprint, manufacturability, thermal modeling of these foam materials. We use, again, conventional, you just use your polymer systems, and then you can put it into a pressure vessel and use the supercritical CO2 conditions to, it enters the polymer, swells it. Then when you depressurize it, it exits the polymer, and that leaves a foam behind. That's the physical situation. And here's kind of the unfoamed polymer relative to its foam. So a great way to lightweight your material and use this environmentally benign manufacturing, lightweighting, much higher volume being created for the same mass that is being utilized. So some
Nandika,
of the,
sorry,
yeah.
one quick question. We have something from Professor Tate. Have you done any biodegradability tests on polymers and composites?
So we use the compostability, biodegradability we have in another, not these composites. My approach is mainly compostability, zero biodegradability, because I want to trigger the degradation. So we monitor mechanical performance over time, because while in use, we want the mechanical properties to be retained, and we use compostability for this paper. For another series, we've done weight loss, which is our biodegradation solution.
Excellent.
Yeah.
Sorry, one more. I think this was a few slides back, but before I forget, on the Kenaf, somebody asked if you incorporate these fibers into a polymer for polymer composites, do you see a degradation of properties when they're immersed in the water?
No. So that, I mean, Kenaf, if you buy it off the shelf, is definitely bad. So we actually recommend a different processing of the fibers. So if you take fibers that are mass produced and you buy Kenaf, that wasn't doing very well in moisture absorption, primarily because your surface is so porous. So the water just wants to go in there and settle in those pores. So you want to try to make a non-porous Kenaf fiber.
Excellent, thank you.
Yeah. So some other applications which you could consider for these is your wind blades. So you would actually have a clean energy and a clean composite. Today, some of the work that I'm going to talk about where we use the CO2 in the building application is we used a microcellulose fiber paired to our corn-based polymer. And that is recently published. And what we did is we took these polymers and we first we looked at the mechanical properties of these polymers. And what we saw is that, I know I could have done bar charts, but I'm going to show you something, which is that we looked at thermal conductivity. Why thermal conductivity? Thermal conductivity is typically ignored by many of us, where we focus on mechanical performance. But thermal conductivity is the key to building applications so that you can have insulation properties. So you want to have insulation properties, you want to have mechanical properties, and you want to have sound absorption. So our current focus is on trying to get all three properties, and looks like we got it in our just slight addition of microfibrillar cellulose resulted in a great improvement in mechanical performance. And we took these polymers and then we looked at the energy footprint. For the energy footprint, we were able to get that the energy consumption. So what do we do? Let me just show you this. So we have the Zero Net Energy House at University of North Texas. And the thing about it is it's a living lab, which means that it's completely digital and you can change any technology in it. You could replace air conditioning, put a new air conditioner in there, and you will get the delta of the energy consumption for that air conditioning. You can have a new temperature controller. You can put that technology in there and you can do that. Then we had another project where some company created a vertical wind turbine. And we put that in there, kind of like little fans all around the place. And that ran, and we would say how much of government or non-fossil-based energy is being consumed. So we are constantly able to monitor what is your reduction in energy consumption from alternative energy sources, what is your energy consumption relative to replacement of materials, because it is completely, the model has been validated. So you're able to switch now material performance characteristics in different segments of your building and see what is the energy footprint impact, what is the energy consumption impact. So this is what we did in the NSF Partnership for Innovation grant. And then now we're only focusing on the foam through using this environmentally benign manufacturing. So here you see that there came at a cost. So we did find that there was a 10% increase in energy consumption from using these bioresourced foams. However, if you start looking at the total footprint, when you're looking bioresources, your total impact is going to be positive because the bioresources is going to contribute to your carbon credits. So that was a kind of our first gamut into this. We've got a current work where we're doing a different combination. And then we were very excited to realize that just 1%, okay, you're looking at 1% by weight of this microcellulose was able to get this carbon, this polymer completely compostable. And so we were very excited by this result, which was a good, a good exciting result for us. So that was our story there. So I just wanted to show you that you can have kind of clean sandwich panels, you can have clean manufacturing and bioresourced materials to decrease your net carbon footprint from your material sources, from your manufacturing contributions, because that's kind of what Dieter Helm is pointing out. When we focus only on one thing without its connections, when we don't include the transportation, when we don't include the harvesting and the manufacturing, etc., we're actually getting only a partial view of the total carbon footprint of a solution. Excellent. So that's there. Yeah.
Dr. D'Souza, we have a question from Dr. Scott Beckwith, who is my colleague. He's SAMPE's Global Technical Director. Dr. Beckwith is asking, can you discuss what FST, flammability, smoke, and toxicity tests tell us about these types of foams, since aircraft, housing, ground transportation, and automotive often are considered for end products?
Yeah. So all the flammability, we actually have a V0 foam solution using, I'm actually going to show it to you for a different reason. So the two bifurcations, not this one is the flammability, but what we did is one approach was, what can we do? Can we use this concept of controlling fibers to do new ideas? One of the things was there was a project related to we all have that, our laptops getting hot. So can we have a thermal pathway, a cooling mat, etc.? So we did this, which was kind of cool, is we found that if you put boron nitride onto your natural fiber, here you have your original polymer, and then here you have your combined system. And then this is your pure boron. So what you see here is that for a substantially lower amount of boron nitride, you're getting a phenomenal bump in thermal conductivity. So I was going to give you this as like, how can you use in what I call designed manufacturing to get new solutions? The other one is we did a approach of multi-layers. Can you use multi-layers paired to our CO2 foaming approach? And we found that using this approach, we can actually make fiber mats that have a very exciting mechanical improvement, but look at the interesting new idea is you can actually create architectures that absorb energy. So you have mechanical stiffness improvement coupled to energy absorption, mechanical energy absorption. And then the one that I was going to give you for your flammability is we created a filler that I showed you earlier about the coating we put on the fibers that was flame retardant. And that material is essentially, it releases it actually releases CO2 during its burning phase, which then quenches the fire, so you can get a flame resistant material. So that's we have a patent on that, a non-halogenated ceramic functionalized material that we would add into the polymer. Let me give you the interesting, additional, exciting solution. When we use this additional material that is flame retardant, we actually also got this wonderful, exciting, this is polystyrene, not our biopolymer, but we bought a concurrent increase in mechanical performance together with the flame retardant performance. So you mix your clay with the polymer, not the regular clay, but this CO2 releasing clay with the polymer, then you put it in your CO2 batch foaming process. The other advantage is, get this, the manufacturing cycle time dropped from 30 minutes to 5 minutes because the surface loves to let CO2 just roll over it, and it permeated through the thickness very fast. So we got a very exciting solution from our, can we get more into this? Now, why did we not do that in this project is because we were, when I presented to you on the energy, was this is a ceramic, so we can still meet the standards. There's an ASTM standards for bio, which is bio-resourced versus organic fossil-based solution. So it's still in the range of being acceptable, but this particular solution does use a inorganic clay inclusion. So that was kind of exciting. So this kind of puts
Professor
together
D'Souza,
some of our journey.
sorry, I was just
Yeah.
going to say, so that's stronger, safer, and more sustainable. I think I read that somewhere in your paper, but so it was achieved.
Yeah.
That's
yeah,
good.
definitely.
That's a great result.
I just want to advocate for that, that we look at problems, we should, engineers, we're problem solvers. So
Right.
just kind of take a step back from all the yelling and screaming and just go back to your science. And the answer is there. Also, feel free to say you don't know. Like I was like, oh, I didn't know about this. And then this student comes back with this blue fluorescence microscopy picture. And I'm like, this is the most pretty picture I've ever seen. And my biology colleague tells me, gosh, that's like plant physiology 101.
Wow.
Well, we engineers need to talk across disciplines. So working with colleagues across, who you may not even like meet for lunches or something like that, convert these meetings into what engineering can I harvest from this person's abilities, and what societal impact that can we both combine to solve. I think it's a great time in our lives to be open-minded and to solve problems. So so this is basically my concluding side, crediting my our funders over the last 12 years. We've got quite a few projects which are non-bio, but in all case, they will be solution oriented. And so I just wanted to present this. Definitely, we would love to partner with small businesses for SBIR grants, for large businesses. We're looking for collaborators to apply to Department of Energy, USDA, etc. We have some ideas for creating a center, because there's none for miles around DFW, that uses these materials. And again, going out of the box,
Right. And Professor D'Souza, I think one thing first of all, this is an outstanding presentation. Thank you for sharing, these impactful results. But first of all, it seems like your multidisciplinary approach is really, you're aligned with this is the future, because there was a lot of bio in here that's a little new to me from a mechanical engineering background. But as you say, within a university campus, any of the colleagues on the call can easily reach out, whether it's to your university or their local university, and start this collaborative approach.
Yeah, I would definitely recommend connecting there's more answers than there are problems, but
Of course.
there are a little bit of challenges. I must admit that sometimes when I get a kind of a function, it takes me a little bit like, we are going to lose this. But let me also throw this in there. We didn't have technologies we have now. Some of these 3D printing approaches, etc. It's it's just getting more and more exciting.
Right. Right. Excellent. I have a few questions from our wonderful group that's actually Nandika has stayed on with us. So I know folks overseas, it might be evening for you already. So we really appreciate it. But first question, do you think we have the supply chain for this type of natural fiber, or is it still evolving?
No, the supply chain is there. I would throw a compliment to our Canadian neighbors, but the Canadian government has, I think, set the blueprint for doing it really well. They embraced the Kyoto Protocol. Because of that, they invested substantial money on the farm to market cycle, and they've embraced the circular economy. But we are definitely, we're just there. It's just a matter of saying the government encourages it and we'll do it.
Excellent. Another actually really pinpoint question from a foam manufacturing company. This is, by the way, from Dr. Beckwith of SAMPE. How do these prices compare to traditional available foams?
So I would say depending on the product, I don't know about the polyurethane foams, but relative to using chemical processing, if you took two different foams for the same polymer, you can say that they are cost neutral because one will use chemical agents and the other one is I'm using physical agents.
Excellent, excellent. I think folks, you may not have heard, but Elon Musk sent a tweet recently on this related topic. So we said to Dr. D'Souza, either she's a mind reader or something's going on, because it's a very timely topic. It's the whole sustainability piece and circular economy in the MNP world. These are things that I think many of the colleagues on this call and our future students, that's what they're interested in. We cannot ignore that. So does it all make dollars and cents? I think Professor D'Souza has showed us it does. So we're really grateful. Are there any other questions from the group? We had a few. We answered a few of them. I still see the majority of colleagues still on, but there's some information in the chat about some websites, the SAMPE website and our next series. If you have some ideas on what you would like to see next, also let us know. Let us know at SAMPE and we will work with you. And some of them may come out of your, company or your lab. And I know Professor D'Souza, as she said, she's open to collaborations. So this is really an exciting time, and that's what SAMPE would like to do. We'd like to facilitate. We'd like to facilitate on these emerging technologies, especially with multidisciplinary communities. Dr. D'Souza, any other comments?
No, you captured it well. I would see that, I think we sometimes change can produce a little bit of fear from the unknown. But, and also I found this part about the environmentalists writing some books and then the industry kind of like not knowing what to do with it has created an unfortunate experience for most people. We don't necessarily need to go completely bio. For instance, last year at a conference, we saw Hyundai. Hyundai replaced all the carbon black across the world with bio-resourced carbon material for its headlights, etc. And next minute, it was like a phenomenal support to all the major automotive companies trying to meet carbon credits in Europe. So while America may not have officially embraced the carbon neutral economy and net zero calculations, the companies have been selling across Europe and Asia. So it is something we will learn. I think SAMPE may get maybe some good insight from our European colleagues or from the Asian colleagues to give us what they've already solved.
Sure. And when, things get back better, the SAMPE platform is extensive. Folks know about the North America activity. We're on a new, digital platform. So if you're sitting in India or in Beijing, it's not going to matter. You're going to be able to participate in the 365 platform for our May event. The October event, the CAMEX, will at this point be in person. So we're really looking forward. But Dr. D'Souza, a few more questions. Everyone so far has been very grateful for your excellent presentation. Here's one from Rick Uskart. Has testing been conducted on matrix composites using these fibers? And how have these matrix materials impacted the compositing results?
We have a good result. If you compare, for instance, polyester with carbon, with the natural fiber relative to the polymers with the glass fiber. So there's substantial publications that have validated using it. There is some little intermediate step that's needed, which is related to fiber treatment. In the composite world, we know so much about carbon fiber and glass fiber. A little more care is needed with respect to natural fiber than commercial approaches. So just
Excellent.
a little cautionary note there, that just kind of treat your fiber so that it doesn't have thermal degradation, and then you'll get great properties.
Excellent. Another one from Dieter Cornett. Do you think that these PLA foams are compatible with epoxy resins?
Yeah, our current sandwich composites are, we're making epoxy carbon skin and these foams and then so we did utilize, let me give a compliment to SAMPE. We utilized some SAMPE recommended interfaces in our lab where we were like, we need a better glue. So they did provide us with some options. So it's you can get it, you can do it, is what I'm saying.
Excellent. Excellent. Thank you. Here's one from, let's see, Bo Wang. I'd like to know more about the fiber diameter, the length of the fibers, the dielectric constant, and the study of porous structure. So here's another PhD candidate for you if Bo already doesn't have it. I mean, thank you, Bo. So
Yeah.
fiber diameter, length of fibers, dielectric constant, and the study of porous structure.
So I'm not sure we've done dielectric constant for that project. We have a different project where we did dielectric constant, but they are in the publications.
Okay, excellent, excellent. I think, folks, at the end of the day, in 1 hour, Professor D'Souza has been probably able to condense maybe a couple of years of significant work and some really meaningful results. So these type of platforms really enable this information sharing, and really that's what it's about, because we would love someone on this call to have the next idea and to collaborate with you, and we'll share your information. You're on Google Scholar, everyone can find you. I know you're a big proponent of our CAMEX show, so if it's in person, you certainly will be there. But we're looking for that. We are looking for you to take this idea and add to it and improve it, and that's what it's all about. Otherwise, why join SAMPE? That's what we want to do. We love your dues, of course, but it's not about that. It's about how can you form this community and solve problems. So I'm going to just about end from now. I'll let Professor D'Souza have the closing remark, but it's really been a great hour. Thank you so much, Professor D'Souza.
Yeah, I just want to thank you for this opportunity. I am a passionate supporter of the professional organization. As an immigrant into America, I consider myself with no phone number on my arrival, and now a plethora of phone numbers and people who can help me, kind of like, what glue should I put on this PLA foam for my sandwich composite? And the professional org is going to be your responder. So I encourage everybody students, faculty, immigrants, non-immigrants, international. We would love to have more engagement with international, scientists and engineers. My point is that be part of the community and impact the world.
That's right. Professor D'Souza, would you be okay if folks on this webinar emailed you for some additional questions?
Yeah.
Okay, great. And certainly, folks, you can do that with us. So my email has been shared. Brianna's email has been shared. We will funnel them. If you have, there's some questions we didn't get to, but please feel free to reach out to us. We will get them answered. I know Professor D'Souza, not only does she run the university, the engineering, on the administration, but she teaches. We were talking about the great new world we live in with all the teaching going online, and we all look forward to having it back somewhat in person. So thank you, everybody. Thank you. And really, we look forward to seeing you again. Consider joining our organization. It's really a modest investment. If you like Starbucks coffee, you like us, so come on, it's a very modest investment. We really want you part of our community. And then if you need to reach out to Dr. D'Souza and her team, we will facilitate that. Thank you, everyone. Thank you. Have a great one.